Hello students, welcome back. Now let's go to section 5, Binomial Distribution 2. Here we're going to talk about some theoretical foundations for binomial probability mass function formula. And these used to be very, very important for probability classes, but times have changed. So nowadays, in 1000 level statistics, it's not being emphasized as much. Anyway, here we go. Let's begin with some concept called permutation. What is permutation? Select R distinct items out of total n choices in order. That's called a permutation. Formula goes like this. For example, out of 10 people, select 4 people in order. First place, second place, third place, fourth place. So, how do you calculate it? P10 4 is 10 factorial over 10 minus 4, so 6 factorial. That's the same as 10 times 9 times 8 times 7. Because, 6 times 5, 4, 3, 2, 1, those are going to be cancelled by 6 factorial down here. So largest 4 numbers. Why? The first place, I have 10 choices because there are 10 people. And then for the second place, I have only 9 choices because first place already is selected. For the third place, I have 8 choices because 2 people were already selected. Finally, fourth place, 3 people were selected already, so I have 7 choices. Multiplying them all up, I have permutation. And in general, this applies to selecting R distinct items out of total n choices in order. Next comes combination. The formula goes like this. C n choose k, or B n choose k, or n choose k like this strange parenthesis notation. They all mean the same thing. N factorial over k factorial times n minus k factorial. So largest k numbers over smallest k numbers. And this thing is called either a combination or a binomial coefficient. And binomial, that's what we are studying here. What is it for? Selecting R items out of total n choices, not minding the order. So instead of selecting 4 people out of 10 and then giving first, second, third, and fourth award, just committee of 4 people. So what's the difference? Well, after getting the permutation, those are, everything in order. I have to undo the ordering of those 4 people. So I have to divide by 4 factorial again. In general, n factorial divided by n minus k factorial is permutation. And then we have, k items in order. Now I have to undo the ordering of that k items. So we have to divide by k factorial, and that's how you get that combination. If you understood, great. Otherwise, never mind, because it's getting really mathematical here. That applies for combination, just ordering versus not ordering. But even more important is selecting R identical items in order. Order is there, but it's just that items are identical. So among those items, I cannot distinguish. So it's the same as not minding the order. But the latter case is rather important because the problem says order, but actually it is not order. Confusing, isn't it? The problem explicitly says in order, but it's not in order because the items are identical and cannot be ordered. Strange, but that's the nature of combination and binomial. Now, if you do not understand that, just never mind and just take it as a formula. N factorial over k factorial over n minus k factorial. How do we apply it? We have 5 red balls, 2 green balls, and 3 blue balls, all right? And let's see. What is the probability to get red, red, blue, blue, and then red when 5 balls are selected with replacement? So no change in probabilities, but in this order: red, red, blue, blue, red. It's easy. For red, 5/10. For blue, 3/10. So it's that, and multiplication is commutative. So we have 5/10 to the third power times 3/10 to the second power. We don't really have to consider any changes of number of balls because it's with replacement, all independent. All right, now this time, blue, red, red. How does that work? It'll be the same. Blue, red, red. But multiplication is commutative, so 5/10 to the third power, 3/10 to the second power, that stays the same. So what is the probability to get 3 red and 2 blue balls in any order? Well, this is one case, that's another case, and there may be more. It's basically the same probability times how many orderings are there. Ordering 3 red and 2 blue. So basically this is selecting R identical items out of total N choices in order. Out of 5 balls, select 3 spots for red. The others will be automatically blue. It's a combination. So what we end up with? Combination 5 choose 3. So 5, 4, 3, 3, 2, 1 times that probability. So 10 times 9 of 1, 800, you end up with this. So the binomial coefficient or combination show up this way. And in general, if this is not just red and blue, but success and failure for Bernoulli random variable, then you're going to get P and 1 minus P. And that's what binomial distribution is. Same thing, combination N choose R, just like this old example. And then success, P to the R power. Failure, 1 minus P to the N minus R power. So out of N trials, if you succeeded R times, the other N minus R times I must have failed because there's nothing else. It is Bernoulli trial, success or failure and nothing else. And how do I order? N choose R. Combination N choose R. Or N factorial over R factorial times N minus R factorial. Do I have those formula there? No, I did not do that here. Yeah. This or that. Those are combination N choose R. And that's how you get the probability mass function and the cumulative distribution function for binomial. It turns out that the means and the standard deviation for binomial turns out to be like this for binomial sum if you add them all up. And for binomial average, from here, divide by n. So np divided by n, so just get p back. Here, we have n inside of this square root. So if we divide by n from outside, then it turns out you're dividing by n squared. So you end up with n inside the denominator. And that's where I'm going to stop. Why we have these, that's a bit tricky story. And precise proof will require, I think, multivariable calculus. And as for the precise computation of these binomials, yeah, we'll do some of those. So don't forget about these. Don't completely forget about those. However, most of the time, we're going to be using approximation using something called the normal random variable, the normal probability distribution, starting from lesson 7. And that's far more important. And this one is just a stepping stone for that. I'm going to stop there.